My name is Ditte Højland. I am founder and CEO in DISSOLVA. As the name suggests, we have a dissolution technology, and this is also what we're working with in the STREP project, our dissolution technology, and see how does this interact with other types of technologies. My own career began more on the creative side. I was supposed to be a fashion designer, but I kept questioning some of the practices in how the textiles are made. And then I decided to go more deep into the technical aspects of production and earn a degree in engineering. So this is seeing the massive waste problem in the textile industry is really what the DISSOLVA was born from. We are a Danish company. We own all the patents and know-how behind our own chemical recycling technology. And this is a technology that really in the short explanation is that we convert blended textile waste, polyester, cotton, and viscose and elastane into high purity polyester granules and cellulose pulp that is used as virgin like quality raw materials for recycled fibers. So during this process, we also remove PFAS, dyes, heavy metals, elastane, and so on. So we make sure that all of these recycled streams are safe both for environmental and downstream uses. My name. Yes, it's a really important and interesting question, I think, because textiles are very complex materials, actually. So we have the natural fibers, the cotton and other cellulosic fibers based on this structural component in plant cells. And it's really a naturally occurring fiber that can then be refined and made into other types of fibers like man-made cellulose fibers. We take the cellulose from wood pulp and refine it into viscose and lyocell and so on. So we have this natural occurring material, but then through a series of chemical treatments, we can make it into a soft thing that can then be used in textiles. But it's very different from synthetic types of fibers. So the natural fibers is more or less a long chain of different glucose units, not to get too much into the chemistry of it. But then we have the synthetics, which are so like fundamentally different materials. So we have this crude oil that we refine into the naphtha, and then we make the petrochemicals. So, for example, polyester, we take ethylene glycol and terephthalic acid, and then we put these molecules together, and we make these long chains, human, man-made, and we have the synthetic materials, but they're so different from the natural polymers. And then when we mix them, and we also combine with many different chemicals that are in general made to make the materials be more endurant, made more thermostable, all these different types of chemicals that we put on, not made to be removed. So when we want to recycle, we really need to take all of these things apart, and we want to do it without actually damaging the material inside. And that's really what's difficult, because they're so fundamentally different, these types of synthetic and natural polymers. So we cannot just apply one treatment to extract them from each other. Oftentimes, the treatment that takes out the cellulose will also destroy polyester and vice versa. So we really need to be mindful on how we approach it. And the way we do it in DISSOLVA, our secret sauce, is that we have this series of very gentle treatments. So we apply one by one. We only target one type of chemical group. For example, first we take from the outside in. First we remove everything on the surface. Then we go deeper and deeper, and these different chemical treatments is it's very mild conditions, but we apply them in a series, so we get everything really nice and clean. And that's also working as a preparation to separate the polymers itself when we get into them. So then we have these solvents that we apply to polyester specifically, and the polyester dissolves, and then we can extract the polyester. It's still intact as polymers, but we can extract these synthetic polymers and participate them in a separate fraction. And then we have this granule of polyester that can be used directly for mill spinning into new fibers. And what is left is the cellulosics, the natural fibers. And just like you can take wood pulp and refine and make that into viscose and lyocell and so on, we can do exactly the same thing with the pulp coming from that process. So that's cotton, and it's also man-made cellulose fibers. They all go back to become man-made cellulose fibers in this new pulp or recycled pulp. So that's the secret sauce. Yeah, so we actually do have this sort of the dry mechanical pre-treatment, we call it, but it's the shredding. So we need to make sure for this chemical process to be very stable. We need to make sure that all the little pieces of fiber that is shredded gets the same chemical treatments. We need a really good homogeneous material. So all the time we get something, we start by shredding it into these small 5-6 millimeter pieces. And then we have these different chemical modules that we apply depending on what's in the feedstock. So we have 2 to 5 different wet processing steps with chemicals, and they are all targeted to specific substances. So it really depends on the input material. So for example, if we have something, we have a treatment meant to remove heavy metals, but we have a fraction going into the process, we know there's no heavy metals in. It doesn't make sense, so we skip that one. And could also be another common example is we have a fraction which is only like a polyester and elastane. So we have some treatments which are really targeted to purification of cellulose. We don't do that. We just remove, we decolorize, we remove the elastane, and then we have the pure polyester directly. So it's actually pretty simple if we know what's in. And then of course where it gets less simple is post-consumer waste. It's almost always very blended. So we might just give it the full spa treatment. The chemicals don't just disappear. We make them disappear so you have to imagine we have these big vessels, tanks with this fiber fluff inside. We pump some liquid of our choosing into the fibers, and this is let's say for example for decolorization. And then we get from that we get this decolored batch of fibers, but then we get the dyes into the liquid stream because we dissolved it. So in our process, we don't actually have a chemical sort of consumption of the chemical. It doesn't react and turn into something else. It's still just like a solvent, like when you wash the dishes, you still have the soap and the water. It's just full of impurities now. So because the dyes there's so little dyes in sort of volume compared to how much liquid we actually have, it takes a really, really long time for this liquid to be saturated. So it can look pretty dark, but it's actually still working really well for, let's say, in the decolorization example, that we can use it for a long time for new batches of textiles again and again. And then at some point it does get saturated more, and we need to clean up that stream. We have this very intricate system of filters and regeneration of the solvent. So we pass it through that one, and then we can put it directly into the treatment unit again, reuse it. So that's how we get this closed loop integration of our solvents. And then, of course, from the filtration of the solvent, at that point we will have a rather small fraction of impurities. So that's both for dyes and heavy metals. It's also for elastane, which is something in the STRAP project. We hope to find a better use for elastane, because right now it is a waste for us. We don't have a way to recycle it, so it could be really good. And then we have this waste stream, and we make sure that we have a specialized destruction for that one. So nothing goes into the environment, but it needs to be destroyed because those chemicals are heavy metals and dyes and so on. They are rather nasty chemicals. It's also the PFAS substances. We have a method to remove PFAS. We need to make sure that there's specialized destruction of the concentrate PFAS from our filtrations. So that's it. And then we have our nice purified raw materials, and we have the solvent going back in for recirculation. The